Welcome to part 12 of our workshop, and we're getting there. At the end of the day, at the end of this episode, we should be able to process at least this top line of instructions, which means we should also be able to process the second line as well. We're going to hold off on SHLD and LHLD to the next episode, and that's pretty much going to round out almost all of these special cases that we need to worry about, which I think is kind of neat. We're getting there. All right, so let's kind of move on. Next instruction here is stax. So stax is going to be hex 2 plus a register offset. Now, unlike LXI, stax, there's only two versions of stax, B and D. So I'm going to do something where I'm not going to be running that offset 16 function. We're just going to check directly, because if someone writes stax H, we don't want to accidentally do the wrong thing. So again, our boilerplate, tokens, output. We want to check. What do we want to check? We want to make sure that there's only one argument. So first should not be empty, and second should be empty. Then we're going to have to do a switch on that one argument that we have. And if it's B, then we're going to say tokens output. Both stacks are just 1 in size. And I'll just hard code 0, 2. And I'm going to do the same thing with D. If we happen to see a D, then our action will be tokens output 1, 12. Just hard code it. In all other cases, we do want to throw a new exception, because we do want to error out. So we say only B or D can be used with stacks. Fair enough. Same thing is going to be true with LDAX. So part of your homework assignment will be to replicate what you do with stacks with LDAX as well. Because again, there is no LDAX H, no LDAX SP. Most of the instructions on this list, you should now know how to work on all on your own. All of these rotations don't take any arguments. They're all 1 byte. And they're all different: RLC, RAL, DAA, STC. So you just line up, right? In this case, 7, 17, 27, 30, 37. The same thing over here: F, 1F, 2F, 3F. Again, we don't have to process these NOPs. And so let's see if there are any left that might require special attention. Well, the Decker, inner, DCX, inks, they all follow the general register offset. So we can say 30, 13, 23, and 33. And again, if we look at our register 16, that will all match up quite nicely for us. Inner and Decker, though, are different than inks and DCX. While DCX and inks increment 16-bit registers, inner and Decker are actually incrementing 8-bit registers. There's an inner B, inner C, inner D, inner E, so on and so forth. So we do need to do something a little bit different for our inner and our Decker. So let's see what that would be. So I'm going to trust that you can do inks and DCX on your own, following the pattern we used before with LXI. I'm also going to trust that you can do these rotations: RRC, RAR, CMA, CMC, RLC, RAL, DAA, and STC. So let's take a look at the inner and Decker. So let's start with inner. So inner is 4 plus, well, kind of a register offset. So it definitely is a register offset, but it's not quite the same register offset pattern as we had before. So let's take a look at it. So inner is going to start with hex 4, right? Because the first time we see INR, we have 0, 4. So B must continue to be 0, because the only way you get hex 4 plus something equals hex 4 is if that something is 0. But how about C? C would turn hex 4 into hex C. Let's see if we can count the number of instructions between. So we have 1, 2, 3, 4, 5, 6, 7, 8. So inner C is 8 instructions after inner B. Could it be as simple as we can do our register 8 function and then simply multiply the result of that by 8, or bit shifted to the left by 3? Let's see. So if we did that, so if this was 0, we get hex 04. If this is 8, right, 1 times 8 equals 8, that would be 0C. If it was 16, right, 2 times 8, then yeah, 2 times 8, 16, or hex 0, or hex 10. 10 plus 04 is 14, and sure enough, that lands us here. So that does appear to be the pattern. The pattern for inner and decker appears to be the starting value, 04 for inner, 05 for decker, and then you add to that the register 8 function, but before you do that add, you multiply the result of the register 8 function by 8, or bit shifted to the left by 3. I'm going to do the bit shifting to the left by 3. So inner would be check, tokens, and we only have one argument for inner and decker for that matter. So we want to make sure the first one is not empty, and we want to make sure the second one is empty. And the action we're going to take is tokens, output, the usual boilerplate. All of our inners and deckers are only 1 byte in size, so we'll say 1. And then the formula for inner is going to be 0x04 plus register 8 on tokens.first and shift it to the left by 3, and that's it, we're done. It's exactly the same for decker, except we start with hex 5 instead of hex 4. And with that, I trust that you should be able to complete, for sure, these first 2 rows. Keep in mind that for MVI, it only takes an 8-bit immediate, not a 16-bit immediate like LXI does. So for that particular case, your immediate should be immediate 8, token, output for MVI. And you'll also notice that MVI follows a very similar pattern to INR and DCR in that there's a B, there's a C 8 away, there's a D, there's an E 8 away. So it's going to be the same logic that we just implemented in inner as well in your MVI. So MVI becomes a mixture of the inner logic with the immediate logic from LXI. And that's it. There's one more thing that we're going to have to do that we'll tackle in the next episode, and that will be dealing with addresses. Once we can deal with addresses, we're pretty much home free. That's the last big thing that we need to do. So let's go ahead and save our work, implement INR, DCR, I guess, and others. And with that, I will see you on the next episode.